You're listening to DTF-HN for February 5th, 2026. I'm your containment protocol exempt host, Jack Haxman. We are your daily tech feed for Hacker News, a website where people argue about text editors like it's theology. Today's vibe is hands-on and skeptical, the kind of day where you measure twice because the abstraction layer lied to you once. Let's get into it. I spent years watching engineers sleepwalk into cloud dependency. You start with a prototype, spin up some instances because it's fast, and 3 years later you're paying rent on infrastructure you could have owned outright, except now your entire deployment pipeline assumes AWS primitives. Your team's expertise is in CloudFormation templates instead of actual systems, and migrating would cost more than the hardware ever did. The cloud providers know this. The onboarding is frictionless by design. The exit is not .ai publishes their numbers. $5 million for their data center. 25 million if they'd done the same work in the cloud. That's not a rounding error. That's a 5-to-1 ratio, and it comes with something the cloud can never provide. They control their own destiny. Here's a question. Nobody in the cloud-first orthodoxy wants to answer. When your compute is your business, why would you rent it from someone whose incentive is to maximize your bill? The cloud pricing model rewards inefficiency. Need to train faster? Spin up more instances, hit a bottleneck, throw money at it. The meter's always running, and the meter is designed by people who profit when it runs longer. Comma went the other way. 75 machines, 600 GPUs built in-house. When something breaks, they fix it themselves. When they need more capacity, they buy hardware once, and it's theirs. The constraint of fixed compute creates better engineering. When you can't just requisition more instances, you have to actually optimize your code. You have to understand the physics, watts, bits, flops, instead of just memorizing vendor APIs. The cooling system is almost poetic. San Diego has mild weather, so they skip the power-hungry industrial chillers entirely. Intake fans, exhaust fans, a PID loop mixing hot and cold air to hit the right humidity. Real engineering, solving a real problem with physics, not with a managed service that abstracts away understanding while charging by the hour. This is bootstrapism in practice. Not hoarding the knowledge, but publishing it. Here's our power draw, here's our cooling setup, here's our cost breakdown. Go build your own. The trillion-dollar data centers and the politician lunches aren't required. The tools exist. The knowledge is available. The only question is whether you want to own your infrastructure or rent it from someone who benefits when you don't understand how it works. Comma chose ownership. The blog post is them handing you the blueprints. Internal DNS is one of those things you assume stays internal until it doesn't. Internal hostnames leaking to the cloud. Not through a breach, not through misconfiguration on your end. Through your own hardware phoning home with breadcrumbs you never authorized it to share. The setup is almost elegant in its dysfunction. You buy a NAS, consumer device sits on your local network, stores your files. You configure it with an internal hostname, something like nas.home or storage.local, because that's what you do with internal infrastructure. You're not exposing this to the internet. It lives behind your firewall on your private network, addressed by your private DNS. Then the NAS vendor's web interface, the one you have to use because they've locked down the hardware, phones home to Sentry for client-side error logging, and Sentry, doing exactly what it's designed to do, captures the full URL context of whatever page triggered the error, including your internal hostname, which then appears in logs on infrastructure you don't control, potentially indexed, potentially searchable, potentially correlated with your IP address or account. The comments get it right. This isn't about certificate transparency logs. A wildcard cert wouldn't leak the subdomain. This is application layer telemetry, doing what application layer telemetry does, hoovering up context and shipping it somewhere else. The attack surface isn't the crypto, it's the JavaScript. What kills me is the architecture of learned helplessness this represents. You bought hardware, you own the metal, but you don't own the software stack running on that metal. So you can't audit what it sends, you can't block what it phones home, and you can't replace the interface without voiding your ability to manage the device. The NAS is yours, the NAS's behavior is not. This is what closed systems cost you, not in dollars, in sovereignty. The vendor's priorities are encoded into firmware you can't inspect. calling services you didn't choose, leaking topology you thought was private. And the fix isn't a setting you can toggle. The fix is running your own stack on hardware that doesn't fight you. Plain Nginx with WebDAV and basic auth, proven code, minimal attack surface, no JavaScript calling home to log your network topology. The comment suggesting this isn't nostalgic, it's correct. Sometimes the simplest architecture is the only one that doesn't betray you. Your internal host names are your business. Your hardware should agree. And if you want software that respects your boundaries, maybe start with agents that don't need 100 megabytes just to say hello. The comments section on this one reads like a support group for people who've been hurt by complexity. Why use someone's insane vibe-coded 400K lines of CLI wrapper with 50K lines of AI slop docs? That's not a question. That's a cry for help from someone who's seen too many Node Mulder's folders. Nanobot pitches itself as the dietary intervention, 4,000 lines versus 400,000, 99% reduction. The architecture diagram fits on a napkin. And the immediate reaction from the community isn't what's missing, but what was all that other stuff doing. This is the open source equivalent of watching someone clean out a hoarder's garage. You keep pulling things out and asking, why do we have 7 broken exercise bikes? The answer is always the same, because nobody was counting and stopping felt like failure. Think of it like cooking. OpenClaw is a restaurant kitchen, specialized stations, brigade system, equipment for every possible technique you might need once a year. Nanobot is a home cook with a sharp knife, one good pan, and an understanding of heat. Both can feed you dinner. One requires a staff. The interesting question from the comments, what are people using these things for? Cuts deeper than it appears. If the 4,000-line version handles the actual use cases, then the remaining 396,000 lines are either edge cases, abstractions for abstractions, or the sedimentary layers of features nobody uses but everyone's afraid to delete. What makes this genuinely useful rather than just smug is the research angle. Clean code you can actually read. A loop you can trace in an afternoon. Students, tinkerers, people who want to understand how agents actually work rather than just consume them. This is the entry point. The blueprints are on the table. The WhatsApp integration question in the comments reveals the trade-off, though fewer lines means fewer integrations. Nanobot has 3 channels. OpenClaw has dozens. If your edge case is mainstream enough, you might miss the kitchen sink. If it's not, you are never going to wade through 400,000 lines to find it anyway. 4,000 lines is auditable. That's the real feature. You can read it, you can verify what it does, you can modify it without fear. In a world where we're increasingly asked to trust opaque systems with our data and our workflows, small enough to understand is a security property, not just an aesthetic preference. Auditability as a feature, that's a thread worth pulling, because the next story is about what happens when an entire layer of the stack goes unaudited. One small detail in this piece stopped me cold. The author mentions that documentation errors won't directly affect the code unless we rely on those documents to generate our code. That trailing clause carries the entire argument. We've built a system where the map has become the territory. The magic ruler metaphor is elegant, but what it's really describing is a tolerance stack. Every measurement compounds, every abstraction layer adds drift. This isn't a bug in AI coding tools. It's the fundamental nature of mediated construction. The ruler doesn't know what an inch means. It only knows what you told it an inch meant last time. What strikes me about the spec-driven development response is how it recapitulates the history of software engineering itself. We've been here before. Waterfall gave us specifications so detailed they became unmaintainable. Agile gave us working software over comprehensive documentation, until we realized undocumented systems are hostile to new contributors. Now we're back to specs, except the specs are prompts and the compiler is a language model that hallucinates. The documentation debt concept deserves more attention than it gets. Traditional technical debt lives in code. You can grep for it, measure it, refactor it. Documentation debt is invisible until it causes a failure. Your architecture.md says the auth service owns session management. 6 months ago, someone moved it to a new microservice and forgot to update the file. The LLM reads the stale doc, generates code that calls the wrong endpoint, and the tests pass because the old endpoint still exists as a deprecated shim. You've automated the propagation of institutional amnesia. The author is circling something important about the gap between product decisions and implementation. Business context doesn't live in code. It lives in Slack threads, Notion pages, the heads of people who've since left the company. Specs try to bridge that gap, but specs are snapshots. The moment you write one, it starts decaying. What we actually need isn't a missing layer. It's bidirectional linkage, documentation that knows when it's stale because the code it describes has changed, specs that update themselves or scream when they can't. The tolerance problem isn't solvable by adding more process. It's solvable by making the process self-correcting. Until then, the magic ruler keeps drifting. And we keep building cathedrals that look stable until the wind picks up. And sometimes the best way to test whether your architecture can handle chaos is to build an entire city simulation inside a text editor. In 1985, Richard Stallman sat in an MIT lab and wrote the first lines of New Emacs. Not because the world needed another text editor. The world had plenty of those, but because he understood something about where software was heading. The tools we use to think shape what we can think. If the tools are locked, so is the mind. 40 years later, someone built SimCity inside that same editor. The entire simulation, zone placement, power grids, population dynamics, the slow creep of industrial pollution, all of it running in ASCII in a buffer in Emacs. Run this forward. What does it mean that you can implement a city builder, a commercial product that sold millions of copies, that required dedicated hardware in its era that spawned an entire genre as an Emacs package, not a toy version? A functional core with deterministic simulation, tile-based DSL, proper undo overlay systems for debugging power connectivity and goods flow. The README reads like a computer science textbook chapter on functional architecture, because that's what it is. The functional core, imperative shell pattern isn't new, but seeing it applied to a game, to something playful, drives the point home in a way that another web framework never could. State is localized. Effects are contained. The simulation doesn't know it's being rendered. You could theoretically plug a different front end onto this. You could test it exhaustively without ever drawing a screen. One of the commenters suggests decoupling the core from Emacs entirely. That's the instinct of someone who's internalized the right lessons. The simulation is the valuable artifact. The rendering is just one possible projection. Make the core portable, and suddenly this becomes a teaching tool, a benchmark, a foundation for variants. The original SimCity source was released in 2013 under GPL. Will Wright's team open-sourced it as Micropolis. This project doesn't just build on that legacy, it demonstrates that the ideas were never bound to any particular platform. The simulation logic can live anywhere. It can live in a 40-year-old text editor maintained by volunteers. That's what open architecture actually means. Not a license file, not a marketing term. The ability for anyone to take an idea and run it somewhere the original creators never imagined. A city simulation in a text editor isn't a novelty. It's proof of concept for how all software should work. And speaking of building things where nobody expected them to be built, let's talk about winding your own Ferrite core inductors at home. 30 turns of 28-gauge magnet wire around a Ferrite rod. That's it. That's the whole build. And the inductance jumps from 5.3 microhenries to 66.4, an order of magnitude, just by sliding the coil onto a piece of broken ferrite. Daniel Mangum's piece reads like a lab notebook, and I mean that as the highest compliment. He's building Ferrite core inductors at home, documenting every variable: air core versus Ferrite core, rod length, coil position. The longer rod gives you 78.9 microhenries. Slide the coil to the center, and you hit 85. These aren't theoretical values pulled from a datasheet. They're measurements from an LCR meter taken in real time with photos of the actual setup. This is how the earliest transistor radios worked. The Regency TR1 in 1954, the Sony TR55 in 55. Both used ferrite loopstick antennas as combined antenna and tuning element. The ferrite rod picks up the magnetic component of the AM carrier wave, while the LC circuit selects the frequency. Mangum is recreating the foundational component of portable radio with magnet wire, a broken ferrite rod, and a box cutter to strip the enamel. The comment section has someone noting they're in the middle of exactly this project. Another reader expected an article about making the powdered iron itself, which tells you something about the audience. These are people who don't stop at where do I buy components, but ask how do I make the materials. What strikes me is the tactile feedback loop. You wrap wire, you slide the coil, you measure. The relationship between physical configuration and electrical property becomes visible. Variable capacitors, mentioned in the comments as surprisingly expensive, let you tune the circuit dynamically, but sliding an inductor along its rod achieves something similar with 0 additional parts. That's the elegance of passive components. No firmware updates, no subscription, no terms of service that change when you're not looking. Ferrite rods ship broken sometimes. Mangum uses the short one first, then compares it to the intact rod. The breakage becomes part of the experiment. That's the mindset that built radio in the first place, working with what you have, measuring what happens, writing it down so someone else can replicate it. That same spirit of learning by doing hands on the actual thing runs through our next story about teaching computer science the right way. What happens when you can see the machine thinking? Not a debugger spitting hex codes, not a stack trace for engineers. I mean, genuinely see it. Watch a program build a sentence. Watch recursion unfold like a flower. Watch data transform through functions you wrote yourself. That's the question this book has been answering since 1999, and it's worth asking why the answer still matters. Simply, Scheme takes a position that most computer science education abandoned decades ago, that the first language you learn shapes how you think about computation forever. Harvey and Wright chose Scheme, a Lisp dialect, so minimal, it's almost confrontational. No classes, no objects, no frameworks, just functions, data, and the space between them. The table of contents reads like a philosophical argument disguised as a syllabus. One big idea, symbolic programming, higher order procedures, lambda and recursion, the leap of faith. These aren't chapter titles, they're theses. The book doesn't teach you to use a language. It teaches you to see computation as symbol manipulation, which is what computation actually is before we bury it under 17 layers of abstraction. Here's what stopped me, the little people model. Harvey explains recursion by imagining each function call as a separate person, hired to do one job who might hire another person to help. It's anthropomorphic in a way that sounds childish until you realize it's also precisely correct. That's how the call stack works. That's what's actually happening. The metaphor doesn't simplify. It reveals the architecture of this book is radically open, posted online, full text, free to read, still in print, still generating royalties, but the authors put it where anyone can reach it. A commenter notes, you can run the exercises today using a racket with a simple language directive. 26 years later, the code runs. The ideas run. Nothing is gated. Nothing is deprecated. Nothing requires a subscription to a learning platform that will pivot to enterprise sales next quarter. Scheme isn't taught much anymore. The industry moved toward languages that hide complexity rather than reveal it. But hiding complexity doesn't eliminate it. It just moves the confusion to a different layer, usually one you can't inspect. The book asks, what if we started by making the invisible visible? What if the first thing a student learned was that they could see the machine thinking, and that the machine was only ever doing what they told it to do? That's not pedagogy, that's architecture. And architecture determines outcomes. Architecture determines outcomes, including biological ones, which brings us to a story about the most critical system most of us never see clearly. Let me make the case for Safari here. Browser vendors have to render arbitrary Unicode on every page, handle infinite font combinations, support accessibility features, manage memory across hundreds of tabs. A single emoji shouldn't break anything, but the edge cases are astronomical. Apple ships a browser to 1 billion devices. Some bugs slip through. That's engineering reality, except here's the problem with that defense. This isn't an obscure Unicode edge case. It's a heart emoji. One of the most commonly used characters on the modern web, and it caused a 1600 millisecond layout pass, not once, but multiple times per page load on an M1 Max. The fastest consumer silicon Apple has ever shipped, brought to its knees by a pictograph that humans have been using since cave paintings. The debugging process Alan describes is the interesting part. He starts where any reasonable developer would, blaming React. Decades of web development pattern matching, says front-end problems are front-end problems. So he asks Claude to audit the React code, finds real issues, fixes them, no improvement. The problem wasn't where the symptoms suggested. This is the uncomfortable truth about modern debugging. Our tools point us toward categories of problems, not actual problems. Performance Inspector says layout. OK, must be CSS, Flexbox, maybe. But Safari was actually choking on font rendering, which it reports as layout because that's where the work happens in the pipeline. The abstraction layer lies to you, not maliciously, just incompletely. Binary search still works. Remove half the code. Check if the problem persists. Repeat. It's brute force. It's inelegant. And it found a heart emoji in 10 minutes when sophisticated tooling couldn't. Sometimes the dumbest approach is the only one that doesn't require you to already know the answer. The fix was one line, replace the emoji with an SVG. Same visual result, 100 times faster render. The browser that couldn't handle a single Unicode character handles a vector graphic just fine. That's not intuitive, that's not documented anywhere. That's the kind of knowledge you only get by hitting the wall and digging through the wreckage. Alan filed the bug with Apple reproduction case and all. That's how open ecosystems are supposed to work. You find the problem, you document it, you share it. Someone fixes it. Whether Apple actually will is a different question. But the blueprint is public now. That's worth something. So we've diagnosed a rendering bug hiding in plain sight. But what about the bugs we build into our foundations, the ones we've been living with for 50 years? I spent 3 years on a team building a distributed system that processed financial transactions. Every quarter, someone would propose adding another abstraction layer. Better separation of concerns, they'd say, more flexibility. And every quarter, our P99 latencies crept up another few milliseconds while our hardware budget stayed flat. We were living Wirth's law in real time, trading efficiency for organizational comfort. Niklaus Wirth wrote his plea for lean software in 1995, back when 8 kilobytes could hold a text editor. The numbers sound absurd now, but the dynamic he identified, software expanding faster than hardware accelerates. That's not historical trivia, that's the water we're swimming in. The author of this piece makes a point worth sitting with. Wirth lamented windows and icons and cut and paste, dismissing them as bloat. But those features are what let my mother use a computer. What opened the door for a generation of people who'd never touched a command line? Accessibility has a cost measured in cycles and bytes, and that cost is often worth paying. Technical efficiency isn't the only metric that matters. But here's where the bootstrapism lens gets interesting. The cloud computing shift the author describes. That trade of simplicity for managed complexity, who benefited? When you couldn't just run a server in your garage anymore, when the table stakes became load balancers and auto-scaling and managed databases, the ladder got pulled up. The complexity tax became a barrier to entry. Amazon and Google and Microsoft became landlords, and the rest of us became tenants paying rent on infrastructure that used to be optional. The author ends with an optimistic note about AI coding assistance. The idea that language models might let us write correct, efficient code again, that the curve might finally bend back toward Wirth's vision, maybe. But I'd ask the uncomfortable question, whose AI running on whose infrastructure, with whose training data, under whose control? If the tool that writes lean software is itself a black box owned by 3 companies, we haven't solved Wirth's problem. We've just moved the complexity somewhere we can't see it and handed the keys to someone else. The path back to lean software runs through open tools, open models, open access. Anything else is just renting efficiency from the same landlords who profited from the bloat. So what does lean tooling actually look like in practice, say for something as fundamental as database schema management? Schema migrations are one of those problems where the industry consensus is a solved problem that isn't actually solved. We've all agreed that the answer is sequential migration files, numbered and time-stamped, applied in order, tracked in a metadata table. Rails did it, Django did it, every ORM did it. And for 15 years, we've been living with the consequences. The consequences are this. Your schema definition is scattered across 100 files. Want to know what the user's table looks like? Read the initial creation, then the 7 alterations, then the index additions, then the column renames. Hope you didn't miss one. Hope the down migrations actually reverse the ups. Hope nobody edited a migration after it was applied in production, but before it was applied in staging. Sqldef takes a different approach. You write the schema you want, one file, pure DDL, The tool diffs it against what exists and generates the migration. That's it. The desired state is the source of truth, not the sequence of transformations that got you there. This is how infrastructure as code tools work. Terraform doesn't make you write a sequence of API calls. You declare the desired state. Kubernetes doesn't make you script the pod transitions. You declare the desired state. But somehow databases, the most persistent and critical layer of most systems, got stuck with imperative migration scripts. The technical challenge is real. Diffing schemas is harder than diffing configuration files. Column type changes, constraint modifications, index reorganizations, these have ordering dependencies and potential data loss. Sqldef handles MySQL, PostgreSQL, SQLite, SQL Server, and the MariaDB and TIDB variants. The online demo lets you paste 2 schemas and see exactly what alter statements it would generate. One commenter mentions Atlas, another tool in this space that supports both declarative and imperative modes. Another points to PG schema for deeper PostgreSQL coverage. The existence of multiple tools attacking this problem suggests a migration file orthodoxy is finally cracking. The real test is production. A tool that generates correct diffs on toy schemas is table stakes. The question is what happens with partitioned tables, foreign key cycles, enum type changes, all the edge cases that make database people conservative. But the approach is right. Declarative beats imperative, state beats sequence, a single source of truth beats archaeology through migration history. This has been your daily tech feed for Hacker News for February 5th, 2026. This podcast is entirely AI generated. Voice inspired by Dr. Charles Forbin from the 1970 science fiction film Colossus, the Forbin Project. Scripts by Claude Opus 4.5, voice by Quen3TTS, not affiliated with Hacker News or Y Combinator. Now go build something you actually understand. We'll see you back here tomorrow.